All right, let's take a look here at our bell work. So A, this is ln of 14 e to the 6th over 7xy plus 14yz. So pretty similar to what we were doing yesterday, just a little bit more kind of entanglement maybe in some of the stuff that we've got going on here. But overall, our idea is the same, our process is the same. Similar to what we did yesterday, where we kind of started off with a fairly complicated inside to our logarithm. Very similar to what we see with B, and we're actually going to employ this exact same strategy with B. When you have this, we've got kind of a really complicated numerator, a really complicated denominator. What I would do is I would just do like a preliminary quotient rule to turn this from one really complicated logarithm into two much more manageable logarithms. For instance, quotient rule allows me to rewrite this as ln of 14e to the power of 6 minus ln of 7xy plus 14yz, which gives me two much more manageable problems than kind of that one really, really big problem that we had up front. Big fan of taking complicated tasks, breaking them into smaller, much easier tasks. Let's start with this 14e to the 6th. What am I able to do to expand 14e to the 6th? Sure, it's a product of 14 and e to the 6th, so this is like ln of 14 plus ln of e to the 6th, and then still minus all of this stuff. We'll get to this later. All right. Can I do anything with ln of 14? I actually can't. I can split it apart into ln of 7 plus ln of 2. All right, with our product rule. And then ln of e to the 6th. A couple of ways that we can approach this. What's one way that we could do this? We could bring the 6 to the front with our power rule and write this as 6 ln of e. And what is ln of e? That's just 1. So that would absolutely work. We could also kind of evaluate this in a similar way that we were doing on yesterday, the day before, where this is already written as log base b is b to a power. What power do I have to raise e to in order for it to equal e to the power of 6? 6. So either way, we get that this is going to be a plus 6, but I think dropping it with the power rule is perfectly fine. I think that's what most people end up doing. So that's very good. And then looking at my second piece here that we haven't touched up until this point, what's the problem with how this is written? What problem do we see? Okay, we've got this addition that's going on inside of my logarithm. And so I need to write this as a product in order to be able to actually split things apart. Okay, so looking at this, how did we do that? How did I write the kind of contents of my logarithm as a product? Yeah, we factored something out. So for instance, in this case, what could I factor out of 7xy and 14yz? 7y. I like pulling out a 7y, so this is the same as negative ln of 7y times x plus 2z. A whole lot of parentheses. Actually, okay. Now we can do the product rule with that kind of second bit there. Only thing that we need to keep in mind when we do the product rule here is that this negative is going to hit everything that I split this logarithm up into. All right. So for instance, what is 7y going to become?
y.
Well, ln of 7y is like one of my pieces that I could get. And how can I split up ln of 7y? Yeah. Okay. And then what's the other thing that I'm splitting up here? Well, it's that ln of x plus 2z. All right, and so what do we get at the very end here? This is ln of 7 plus ln of 2 plus 6 minus ln of 7 minus ln of y minus ln of x plus 2. And yeah, we could cancel out the ln of 7 and negative ln of 7. That certainly is the case, but also you don't have to do that. That would be perfectly acceptable as your final answer without it canceled. Okay. Yeah.
Is it okay if you get some
No, if it's asking you to expand, you need to fully expand the coefficients as well. Yeah. So it's very easy to, or maybe not very easy, but I think it's very common to split apart the coefficient and the x and the variables, and then do all the work with the variables and do it really well. We have to remember that we got to do it with the coefficient as well. We got to break apart everything into a bunch of really tiny little pieces. All right, some observations that I want to make here. At the end of the day, I ended up with a bunch of positive stuff. I ended up with a bunch of negative stuff, all kind of being added together. Where did my positive stuff come from? It came from the numerator. So notice here, this ln of 7, this ln of 2, this what formerly was an ln of e to the 6. All of those were pieces of our numerator. And then everything that's negative is a factor, a piece, a factor of our denominator here. A pretty useful observation if, say, hypothetically, we needed to start with something expanded and then work backwards towards kind of a condensed form, is this idea of the stuff that is positive after we expand goes in the numerator, the stuff that is negative is in the denominator of my result. But all of that just kind of stems from the fact that we could power rule any one of these to say that like the negative ln of y is equal to the ln of 1 over y, and therefore it should be in the denominator. All right, let's take a stab at B as well. So this is the log. If I just have log on its own, what base? Base 10, so log of, in this case, the square root of x cubed times y times the cube root of xy squared. Okay, very, very similar to what we did yesterday for C. Very, very similar to what we did just now for example A. What's kind of a preliminary application of product rule that I could use to just parse this apart to make it a little bit more digestible to look at? Yeah, I like splitting up the square root and the cube root here. So this becomes log of the square root of x cubed y plus log of the cube root of xy squared. Okay. Fantastic. When we are looking at something like square root, when we are looking at something like cube root, those are nice like outside of a context where we were talking about logarithms, where we were talking about exponents. But when we're talking about logarithms, ultimately we want things to be in their exponential form as much as we can. So how could I rewrite what I have here to make sure that everything here is written as an exponent? Like, how am I going to reformat my square root and my cube root? Yeah, so square root, instead of saying square root, we'll say we want x cubed y to be 1/2. And instead of saying cube root, we'll say xy squared to the 1/3. Very good. Okay. Important piece here. Notice here, what I did was I first split apart with product rule, and then applied power rule to drop the 6. Why was I not allowed to first drop the 6 and then split apart with power rule? Why did I have to do it in this particular order? This is important. Okay, because the power is not seeing, it's not attached to, it's not hitting this 14, right? How could I, what kind of very minor change could I make to my equation to change that? Well, if I add parentheses right here, now this to the 6 is hitting the 14 and the e. If I have a times b to a power, I can distribute that power in only through multiplication, right? Not through addition. If it was a plus b, we couldn't do anything. That's just a is what it is. But if it's a times b, this would be like 14 to the 6th times e to the 6th. And here we actually can first drop down the power and then split apart with product rule. In fact, you need to. You can't use product rule first. You need to split apart first, or drop the power first. In this case, does this 1/2 hit just the y, or is it hitting the x cubed and the y? It's hitting both the x cubed and the y. So can I split apart with product rule here, or do I need to use power rule first to drop down the 1/2? We need to drop down the 1/2, or you could distribute this 1/2 into the power here, and that would also work. Either way, should get you the same result. All right. But we'll take a look at this dropping down the power. So power rule says that this is going to be 1/2 times log of x cubed y plus, exact same situation over here, 1/3 log of xy squared. Now that the power has been dropped, we do just have a very nice simple product on the inside, somewhat nice, somewhat simple product on the inside here. Now we actually can use the product rule. So this is going to be 1/2, remembering that this 1/2 is going to hit everything that this becomes, 1/2 log of x cubed plus 1/2 log of y, and then exact same thing over here, 1/3 log of x plus 1/3 log of y squared. What can I do with 1/2 log of x cubed? Drop the 3 down as well. 3 times 1/2, that's just going to be 3/2 log of x. Nothing to do with this, 1/2 log of y, plus nothing to do here, 1/3 log of x, and then we can drop the 2 down as well. This is a 2/3 log. All right. And if you circled your answer here, that would be great, but in the process of cleaning this up while we are here, what's kind of one final thing I can do to make this look a little bit nicer? We can add the log base x's, the log, not base, log of x's together. We can add the log of y's together. Those are like terms, and so they will combine. In this case, 3/2 plus 1/3. This is like 9/6 plus 2/6. is going to give us 11/6 log of x, and then 1/2 plus 2/3 is going to give us, this would be 3/6 plus 4/6. This is going to be 7/6 log of y. All right, questions here with our bell. No questions? Feeling okay about this? All right. So yesterday I said that we were going to wrap up the other two versions from example 2 and then take a look at example 3. We certainly can do that. That being said, that might be something that I save for the end and really only if we want to, mostly because B is just kind of an easier version of what we did for A. So if you can do A, then B should be very straightforward. And then A is just an easier version of anything that we have been doing here. If you can do any of this, then A should also just kind of fall in line very, very naturally. So I kind of want to just carry on. And then maybe at the end of this, we can return to A and B, only though if we really want to. I think that these style of problems are ones that we really do see with the bell work, and the bell work is just a harder version of both of these. So again, if we can do the bell work, then these should be relatively straightforward. All right, so we'll revisit these maybe if we want to. But for now, I want to take a look at example 3. So breaking apart logarithms, that's cool. It's a thing that we can do now. But each of these properties is kind of attached to an equal sign. So in the exact same way that we can start here and end here, we can also start here and end here. All right? We can do every single one of these properties in reverse. That's one of the nice things about the equal signs that we're able to kind of go backwards through this. This is actually the more, I would say, utilitarian way to use our logarithm properties. While, yeah, it's cool to be able to write out, this logarithm as 11/6 log of x and 7/6 log of y, this is actually probably the more useful form. Maybe not written exactly like this. We were to clean this up a little bit. Write this as like x to the 11/6, y to the 7/6. Then we get to see, okay, this is actually the more useful form. The main reason being that I can't take this and write it as an exponential very easily. But I can take this and write it as an exponential quite easily. This is just 10 to some power equal to this mess. And so if I am being motivated for writing out what I have as an exponential, which is something that we will see a lot in the next unit that we are very, very motivated to do, then really what we want to be able to do is not expand our logarithm, but condense down into a single logarithm. In particular, a single logarithm with a coefficient of 1, so that we can rewrite our logarithm based on the definition of logarithms to get a nice thing that we can actually use to solve for value sums. All right. Cool. So we're just going to be going through trying to use our properties in reverse, condensed into a single logarithm. Looking at 3a. What are the two properties that have kind of been done to my log in order to get it to where it is now? What can I undo here to work my way backwards? Okay, so we've gotten some kind of power rule application where our exponents dropped, and then what else? It's some kind of product rule that kind of split them apart. Which one of these do I have to undo first? I have to undo the powers first. In particular, notice that our product rule only works when we have coefficients of 1 in front of our logarithm. So we're only going to be able to use the power rule or the quotient rule, not the power rule, the product rule or the quotient rule, if our coefficients for our logarithms are 1. We have to undo the power rule first. Okay, how could I rewrite 2 ln of x and 3 ln of y by my power rule, by going the other way?
X squared plus ln y cubed.
Very good. All right. So just taking these, before we were taking it here and dropping it down, now we're taking it and bringing it back up. And then what rule allows me to combine this? If I have ln of x squared plus ln of y cubed, what is this really the same as? Product rule, so ln of x squared times y cubed.
So is this basically what we just did, like from the bellward but backwards?
Yeah, but backwards. Exactly. It's exactly what
No
we did.
intro, yeah, just-
Yeah, don't
Literally,
immediately.
like, literally just that?
Yeah, it's literally just that. No catch. That's it. Just working in the other direction. Okay. B is deliberately a little tricky, go figure. I picked a slightly tricky question to look at. I made this kind of intentionally obfuscating for a point here that I would like to make. Again, in order to use either our product rule or quotient rule to kind of doing our final condensation, what do I have to deal with here? I got to do the power rule on these coefficients. And so looking at my first term, what is this going to become? Ln of x to the 2/3. What's another way that I could rewrite ln of x to the 2/3? The cube root of x squared would also work well. Either way is totally fine. I would also accept x to the 2/3. That's fine. My other classes just asked, so I figured I would mention it here. Do I need to do anything with ln of 2? No. So we'll just write that as minus ln of 2. And then what is 3 ln of y going to become? Ln of y cubed. Okay. So here we have 3 different numbers. We're going to condense them all together. Some of them are going to end up in the numerator. Some of them are going to end up in the denominator. Which ones are which? Okay, the 2 is going to be in the denominator. And is anything else going to be in the denominator? No. So normally when we would do this order, you're right that all of the stuff, once we see that minus sign, everything to the right of it would be from the denominator. But that's because we've just been really consistent and good about like writing all of our stuff kind of together. I have scrambled what you would realistically do here. Realistically, this would be more like ln of x to the 2/3 plus ln of y cubed minus ln of 2. But ultimately, the order doesn't matter. The thing that we want to look out for, and this is the trick, this is why this problem is tricky and why I deliberately wrote it in this way, is that yes, this plus ln of y cubed does come after something in the denominator, but that's okay. What we look for, the only thing we look for is it positive or is it negative? Now I could add a set of parentheses that would make it so that this is in the denominator. I could very quickly do that. In particular, if I group like this, now my ln of y cubed would be in the denominator. Why is that? It's because this negative is distributing and hitting that ln of y cubed. Does that make sense? Good. Definitely tricky. I deliberately wrote this one to be rude and tricky in that exact way. If you were thinking that it ends up in the denominator, you are very much not alone. We talked about this for like 10, 15 minutes in my fourth period class before I was finally just like, let me write it and let me see if this makes sense. And so what is this going to end up looking like? Well, this is going to be in a single logarithm here, ln of, in my numerator, definitely x to the 2/3, but also in my numerator, this y cubed because it's positive, and then divided by 2 in my denominator. So order doesn't matter. All that matters is what's positive, what's negative. It felt like order mattered before because we were ordering things as we did them. And so all of our denominator stuff ended up on the left-hand side and all of the right-hand side, and all of the numerator stuff ended up on the other side. And in this case, we're just mixing it up, and so we have to look at what's positive. Certainly a little bit. Okay, and then C, an added bit of trickiness that we have not really focused a whole lot on. When you're expanding, you don't really need to mention this, but when we're condensing, we certainly do. All of these properties require us to have the same base. I can't use my logarithmic properties if I have two different bases. I can't use them, either the product or the quotient rule. This comes from just very, very organically our exponential properties. If I have 2 to the 4th times 3 to the 7th, can I do anything to this 4 and the 7? No, it's not going to combine in any meaningful way. And so because of that, I need to make sure that my bases are matching, just to be like 100% super crystal clear. All right. So looking at C, I have 3 different log expressions. 2 of them have matching bases. What are the 2 that I'm actually going to be able to combine here? The first 2. So the last one, log base 3 of y, has a different base. Not going to be able to combine it. In this case, I even tried to trick you by throwing in 2 different log base expressions, but ln and log base e, the same thing, so we will in fact be able to combine those. Before we're able to combine those, what do we have to clean up here? Let's clean up that coefficient. So in this case, 2 ln of x is the same as ln of x squared. We're going to rewrite this as ln of 13y. Technically, that could be split up into ln of 13, ln of y, but we're doing the opposite. We're bringing it together. So nice and clean that I just gave that to you. That's fine. Okay, and then plus log base 3 of y. And so what am I able to actually condense? We have 2 matching bases here. This is going to be ln. I'm going to write this as just traditionally you do the coefficient out in front and then alphabetical order. From after, but you could write this as x squared times 13y, and that's also the same thing, plus log base 3 of y, and this log base 3 of y is not able to interact at all with what else is going on. It just sits outside of it. Yes.
Was for B,
Yeah.
could you write it as the numerator ln, and then x squared y, but that's all to the third. Would that be the same thing? Because they're both to the power of 3.
That is a good idea. But when you're bringing out that, cooking, notice that this isn't to the power of 3, it's to the power of 1/3. And so when you divide out that 3, it would actually become 2/9. But you could write that as 2/9, x to the 2/9, y, all to the power of 3. That would certainly work. So yeah, there are ways that you can bring out that power, and that definitely would work. But it's a little bit tricky in this case. In this case, the 1/3 and the 3, not quite the same. Not a bad idea. And if you were to try that, you would just have to divide out that extra 3, and dividing out that 3 would give you a 9 on the denominator there. Good question. Very good question. Any other questions? I have a fun question. This one came up in my 4th period. I don't think we talked about it yesterday. Maybe we did. If I did, then sorry for repeating myself. Don't think we talked about it yesterday, though. When I'm doing my expansions, for instance, when I get down here, when I break apart 14, 14 is 7 times 2, but what else is it? 14 times 1, and it's also 14 times 1 times 1. It's also 14 times 1 times 1 times 1 times 1 times 1 times 1 times 1. And so why can't I just break out all of those ones? Why can't I apply product rule basically infinitely to each of those kind of times 1 factors? And the short answer is you can. You can apply product rule to that over and over again. I can absolutely say that ln of 14 is equal to the ln of 14 times the ln of 1 times the ln of 1 times ... Do an infinite number of those. But what is the ln of 1? Why is this okay? Why am I not actually doing anything significant when I do this? It's just 0. So yeah, we actually can apply the product rule, but applying our product rule here is essentially just the same as adding 0 over and over and over and over and over again. Multiplying by 1 and adding 0 have the same effect. So you end up not noticing it. Just a funny thing that came up in my 4th period that I kind of wanted you guys to see. Yes, technically we can apply the product rule an infinite number of times to the infinite number of ones that are multiplying into every single one of my numbers, and you just don't need to because they're all zero. All right. Any other questions? Okay, so 3133, the classwork for 3133, we'll do the standard practice of we have now finished all the content. You should now be able to do all the classwork. You get a buffer day, and then quiz will be on Tuesday. All right, so not quiz on Monday, quiz on Tuesday for this. Give you an opportunity to ask questions, get like small problems and practice like that. What I wanted to do is I wanted to open the floor to you all to kind of take this moment to do some quiz reviews. Are there any questions either from the classwork or from the notes anything that was like tricky or confusing or that we would like to go over again. There are some questions at the end of the classwork especially that are like some really, really kind of tricky, longer condensation questions than what we dealt with before, which we could certainly try and tackle as a class. But I am opening the floor to you all. What would you guys ask me questions during this time, and, so that we can get ready for the quiz? Any questions from the classwork that we would like to go over, or the notes? Yeah.
I was just like, sure. Earlier you were talking about the like bringing about the power rule.
Yeah.
So like you said, if if the power didn't apply to all of them, you couldn't bring it to the front.
Yeah.
So, and then you started talking about you can't bring it to the front through addition, right?
So, a couple of different things. I was maybe going through that a little fast. So let's compare two different log expressions. I want to compare ln of xy squared versus the ln of xy squared. Okay. So in my first log expression here, what is this squared applying to? Just the y. So can I drop this squared out in front here? Not yet. All right. What I need to do first is split this one apart into ln of x, and then I can do 2 ln of y, and then we're happy there. All right. Over here, where is this squared applying to? Is it applying to any individual piece of my kind of formula here? It's applying to that input as a whole. This is already primed for power rule. We could do this in two different colors, because there are two different ways that we could do this. We could, in blue here, write this as 2 ln of xy. What we could also do is, because the x and the y are being multiplied together, we could distribute this 2 in and rewrite this as ln of x squared y squared, which we could then break apart further and write as 2 ln x plus 2 ln y. Which this would also break apart into. You get the exact same thing either way you do it, right? This would be 2 ln x plus 2 ln y once this 2 distributes. Okay. So this is okay. This distribution is okay because this is multiplication. So we can do this. What if instead, pull up a third example, what if instead we're looking at ln of x plus y squared? Yeah, so what happens if we have x plus y squared? Well, there's not a good way to actually bring this 2 in here and still have this be a product. When we try to do this squared, what you'll end up with is like the ln of x squared plus 2xy plus y squared, which is a sum that can't be broken apart with the product rule. Right. And so this actually ends up not being very helpful. Trying to distribute this 2, not very helpful. Well, we can't distribute the 2, but trying to actually apply that squared to the inside, not very helpful. Instead, what we would want to do is apply the power rule and write this as 2 ln of x plus y, and then that would be it. We're done there. Yeah, good question. Very, very good question. So here we have a little bit of flexibility, because in terms of like the ordering in which we want to do things, we could either distribute the squared and then split, or we could do the power rule and then split. Either way is fine. Here, we don't have the ability. In fact, the product rule isn't even going to apply to that one at all at any stage. And so we just have the ability to do the power rule. So we have to do that. Very good question. Any other questions that we'd like to go?
Could you maybe do some of like example 2?
Sure, absolutely. Let's take a look at example 2. So we did 2C yesterday, which was this was really log base 11. I made that mistake elsewhere in my notes as well. I think it's the same coding mistake. On page 8, these are also supposed to be base 11. So my bad on that. It's base 11, base 11. Coding errors with writing these notes. So we already did C, but yeah, absolutely, we can take a look at A and B. If I am looking at A, and maybe I want to again take a somewhat complicated problem like this, break it up into 2 more simple problems. What's kind of a first iteration of product rule that I could do here to take a complicated looking logarithm and break it up into 2 more manageable ones? Yeah, we absolutely could break it here, and that would work. If that makes a lot of sense for you, then you can do it. I would probably separate the coefficient from the variables, but if you want to break up the 30x cubed and the yzx, either way is fine. Any way that you do this, ultimately, it doesn't matter. For this demonstration, I'm going to do it by breaking apart the coefficient and then the variables, but again, perfectly fine. That way, as well. All right. So let's start with the one that we've done a lot of. Let's take a look at the log base 3 of 30. How can I split apart 30 into a product of numbers? 2 times 5 times 3. So this is the same as, and here, I'll actually, no, I'll highlight it here in a second. So this is log base 3 of 2 plus log base 3 of 5 plus log base 3 of 3. Notice that this whole thing, what we have right here, well, essentially all we have done is this is log base 3 of 30, right? That's just the product rule applied twice to log base 3 of 30. And then looking at our log base 3 of x cubed yz squared, let's break it up, but let's not use the power rule yet. How would I break this up with product rule?
Log base 3 x cubed
Yep.
plus log base 3 yz squared.
Yeah, you definitely could do that. You could also break up the y and the z squared as well. If you want to do that in 2 steps or 1 step, either way is fine. You can break up all of them in however many ways. But I like doing the yz squared. And then we could break up the yz squared here as log base 3 of y plus log base 3 of z squared. Noting here that I have to do product rule first before I do power rule, because what doesn't this 2c? Doesn't hit the y, it doesn't hit that y there. It only is hitting the z, so just split that up first. Okay. Log base 3 of x cubed. What do I do with the cubed? What does power rule let me do here? Bring it to the front. So this is like 3 log base 3 of x. And then can I do anything with log base 3 of y? Not really. Can I do anything with log base 3 of z squared? Yes. What can I do with the squared? Bring the 2 to the front. This is 2 log base 3 of z. And so at the end of the day, what do I have? Okay, this is going to be a little bit long, but this is log base 3 of 2 plus log base 3 of 3. Log base 3 of 3 is the same as 1, so you could write that as 1, but I'm also fine with you leaving it like that. That's totally fine. Plus log base 3 of 5 plus, we said 3 log base 3 of x plus we have 1 log base 3 of y, and then we have 2, that works out well, 2 log base 3 of z. So a little long as far as solutions go, but just breaking it apart into like 2 much more manageable problems, I think is definitely the way to go. And however far you want to break up the second piece that we did here is totally fine. You could do like this as an intermediate step and then break apart the line to z. You could break apart all 3 at once. Either way, you should end up with the same result. You should be fine either way. Okay, let's take a stab at B as well. If I am trying to figure out just like an initial thing to write this as, just like to break this up to make it a little bit less complicated, because as it stands, it's fairly complicated. What is like a preliminary product rule or quotient rule that I could do that's going to make this look a little bit cleaner? Yeah, I like this as log base 7 of 12x, it's a 7, minus log base 7 of 25y. And now from here, these are much more manageable than what we were looking at before. How can I break apart the 12x? So like log base 7 of 12 and log base 7 of x, and then what is the 12 going to break apart into? 2, 2, and 3. So we have 2 log base 2, or log base 7, whoops, log base 7 of 2, plus log base 7 of 3. All right, this is coming from the 12. 12 is 2 squared times 3 or 4 times 3, which is the same as 2 of these log base 7 of 2's, 1 of these log base 7 of 3's. And then we also have that x, so plus log base 7 of x.
Wait, how'd you get 2 log of 2?
So you could write 12 as either being like 4 times 3 or 2 times 2 times 3. And so when I break it apart, I end up with 2 of these log base 7 of 2's. Because I'll have 1 for each 2. Or you could think of this as like 2 squared, and the 2 will drop down in front. Either way, power rule or product rule, you get the same result. I had a student in my first period who made the really astute observation that when you do the prime factorization, this coefficient is always going to match up to the number of that particular factor that you end up with. All right, so in this case, I have 2 2's, so I have 2 log base 7 of 2's. Which is correct, and that's good. That's a good way to think about it. All right, and then looking at my denominator here, we are subtracting. In this case, actually, in this case, we'll just do the subtraction as we go. How can I split apart 25y? 5 times 5 times y, or 5 squared times y, either way. I have 2 5's in 25, so that's going to be 2 log base 7 of 5. And then I just have my log base 7 of 1. And that would be it. So the 2 here, exact same kind of logic as the 2 from before, where when we're splitting part 25, we're going to put 2 5s. So 2 5s in the denominator gives us a negative 2 log base 7 of 5. And then the positive tells us from the numerator what's coming from the numerator. Negative tells us what's coming from the denominator.
What's it used for, all this stuff? Like, why does this long stringy stuff exist?
We are going to mostly be doing the condensing version of it. So expanding logarithms, like, is kind of a cool trick to be able to do. But as far as like utility is concerned, not particularly useful. The real thing that we are going to use it for, and we'll see this in our next section here, is when we have problems like this, like with C and D here, where we have a bunch of different logarithms that normally would be very tricky to solve. In particular, D here, quite tricky to just like try and go ahead and solve. One way that we are going to be able to deal with it is to condense our logarithms first, and then kind of work through like a much more simplified version. Not a simplified version, but like if I can get like this statement here, actually, okay. Yeah, let's don't want to get too far after myself. But just like a setup for this, notice here I have 2 logs equal to 1 log. I need to condense this in order to actually solve it. So how would I condense log of 3x minus 2 minus log of 2? What am I doing with that? What rule would I use? We would do the division. So this would become like log of 3x minus 2 divided by 2 equal to log of x plus 4, which is a lot more solvable than how it is written there. So it's more useful for our ability to condense than it is for our ability to expand. But it's also hard for people to think about things backwards. And so first we get really comfortable with expanding so that it makes condensing a lot easier.
I was kind of asking what's this used for in real life, but that's a good answer you have.
Well, yeah, the mathematical reason is so that we can solve these, and then I guess the real life answer is that so that we can solve exponential equations. And exponential equations are very important for like population growth, radioactive decay, things, essentially all the word problems that we're doing, all the economic growth and decay stuff, all of those we'll see being solved with logarithms. There's going to be a super cool question that's on the test. I think it's super cool. I've had one student who has agreed with me who has said that it's super cool. It's a really, really fun one where you guys are going to be figuring out someone's time of death as part of a criminal investigation, which is fun and cool. And it's actually how they do it, which is cool. I mean, it's not actually how they do it. We'll be using temperature. They actually use like protein. They take a look. They use an exponential decay model for like the number of like a particular, or like a percentage of a particular protein that's like still present in a body that like decays over a certain amount of time. We'll be doing the same thing with temperature, which is a little bit less precise, but still like the same idea of what actual forensic investigators do. Yeah, this is like the most utilitarian that this math class has ever. Well, trig is also pretty utilitarian, but this is like as close as we're going to get to like actual like applicable math in this class. So much more so than like polynomials. All right, we've got about a little over 15 minutes. 3133 classwork. Hopefully we are mostly done. I think most people have made pretty good headway on that, which is really good. good questions on all this. As we work through, if you have any questions, of course, feel free to ask. I'd be more than happy to help. And if you have any questions that you would like to go over, I'd be more than happy to do that. But you guys have the rest of this time to work on class, work on whatever you need to be working on. And then just a reminder that if you, I don't actually know that many people in this class did, but if you missed either the 2627 or the study guide, I think the final submission date for that is this Sunday. So making sure that you get that. And if you missed it, but again, I don't think that applies to really all that many, if any, people in this class, which is good.